welcome you to my lecture today. Today, we're going to focus on another fascinating statistical topic. Uh, we call this comparison between groups in Bertalanffy growth models. Of course, on Monday, we started nonlinear model. And one of the nonlinear models we have around is Bertalanffy. So, and I remember on Wednesday, we focus on, the Bertalanffy model, okay? But today, we're still going to talk about Bertalanffy model, but how do we compare groups, two different groups, using the Bertalanffy group model? That's going to be the focus today. So, in the outline, I'll review Bertalanffy group model. Then we're going to go straight to the business of comparing groups using the Bertalanffy growth model. Okay. You remember when I was specify the Bertalanffy growth model the other time, I walk you through how to derive the Bertalanffy growth model from ordinary differential equation. Okay, we solve ordinary differential equation, we arrive at the mean function for Bertalanffy. And don't forget, we got three parameters in Bertalanffy. We got L infinity that I call asymptotic length, asymptotic mean length. And we got K, which is Brody growth, and we got T0. And of course, I actually apply that to, data on fish. I remember on Wednesday, we concentrated on male fish, where I walk you through how to estimate parameters in the Bertalanffy growth model. Of course, we also test assumptions using with the Bertalanffy growth model, just like every other statistical model. Bertalanffy growth model also have assumptions of normality, assumptions of constant variance, okay? Even though we know assumptions of independence will be violated because we're working with a time series data. I remember I walk you through how to investigate whether a certain assumption is violated. Okay, why is that important? Assumptions of normality, assumptions of constant variance, they are very important because it is when error behave well that we expect the distribution of the parameters in the Bertalanffy growth model to follow normal distribution. Okay, and that was why we investigated the normality assumption using the histogram of residua. We investigated the assumptions of constant variance using residual plots. Do you know what the assumption of constant variance is talking about in the context of fish? Don't forget, we are relating the length of fish with the age of fish. It's trying to say the variance of the length of fish given any age of fish should be constant. We know that that may not be true because smaller fish, we expect them to look alike in terms of length. And we expect bigger fish to look alike in terms of length. So we expect there's basically going to be a violation. Now, how do we fix violation? I think I walk you through that. If you want to fix violation, violation of what? Violation of normality or violation of constant variance, we need to consider how error enters a van Bertalanffy growth model. You know, when error enters additively, we had a violation. But when error comes in multiplicatively, which I call the log normal error structure or a multiplicative error structure, we realize that the problem was fixed in a way. But what do we want to do today? Within the van Bertalanffy, we want to compare lengths. For instance, is the length of female fish the same as the length of male fish? That's what we want to compare. We should call the comparison between groups. But if we want to compare, don't forget, in van Bertalanffy growth model, we got 3 parameters. Now the question is going to be, should we consider a model where they have separate values for the parameter, the 2 groups, that we're actually going to call a general model? Or should we consider a model where they have 1 parameter in common? I'm referring to the 2 groups now. Whether, okay, they're going to have, maybe they have K in common, or they have T0 in common, or they have L infinity in common. Or should we consider a model where they have 2 parameters in common? Or should we consider a general model where they have separate parameter common? So which means in an attempt to compare 2 groups, we're actually going to have a lot of models. And you know what? The idea of a nested ANOVA that we use in linear regression will be used here. Does that make sense? In selecting the model. But let me tell you this, because we actually going to have a lot of models. Before I continue, those of you online, can you confirm if you are hearing me clearly? Okay, thank you so much. Thank you for confirming that. Now, because we're going to have a lot of models, where we want to compare the 2 groups of fish, then we need to begin by testing whether absorption hold. In statistical analysis, we actually cherish absorption a lot, because before we can trust our model, absorption must hold. Now, since I got a lot of models here, you know, if I want to compare 2 groups of fish, then I can start with the general model. When I actually test absorption in the general model, what do I mean by general model? The general model is when I assume separate parameter for the 2 groups. Does that make sense? Separate parameter for the 2 groups. Okay. So when I conduct the absorption, when I check the absorption with the general model and the absorption hold, then that will imply that absorption will also hold with the sub-models. Does that make sense to every one of you now? Now, what I want to do now, I first want to go through the van Bertalanffy group model. I need you to look at equation 14. Oh my God. The equation 14 is van Bertalanffy growth model for group 1 and group 2. There's something I want you to take note. take a look at the H parameter in that module specification. The L infinity is trying to tell you the L infinity for group 1 is different from that of group 2. You are using separate, and when you take a look at the K, also different. You can see we indicated 1 and 2, right? And when you look at that of T0, we also indicated 1 and 2. You know what I mean? This is comparing two group with a separate parameter, separate values of L infinity, separate value of T0, and separate value of K. Any question? That's a general one. Okay? Another way I can write the general one, if I don't want to write it and indicate group 1 and group 2, I can rewrite it as, look at the equation 15. That's another way I can write that. Take a look at that, equation 15. You can see that I put group on L infinity, right? I put group on K. I put group on T0. Take a look at that. Putting group on them actually means if group equal to 1, I'm talking about group 1. If group equal to 2, I'm talking about group 2. Any question? Okay, now you understand what equation 14 and 15 is talking about, right? They are the same. Equation 15 is another way to write equation 14 if I don't want to replicate the Bertalanffy for the two groups. Okay, now this is a general model, one of the models when we want to compare two groups. Now let's look at the other subset models. Okay, but before the subset model, if you take a look at the first one, that's a general model, right? Now, number one is general model. The second one is going to be if one parameter is common between groups. If one parameter is common between groups, how many possibilities are we going to have? That will be 3, right? Don't forget we got 3 parameters. Okay, so if you take a look at the way the specification is done when L infinity is common between the two groups. What are you going to see? I want you to focus on this model now. Do you say group on L infinity? No, no group. It means that is common. But when you take a look at the other parameters, you're basically going to see that there's a group attached to K, there's a group attached to T0. So here is just talking about it is only L infinity that is common in two groups. Does that make sense now? Now, when you take a look at the common K, take a look at K. Okay, you are not going to have group for the K, but you're going to have group for the other parameter. So this is a situation where K is common between two groups. Now, what about when T0 is common between two groups? This is a model specification. Any question? Because what if I ask you to specify model? Okay, when we're comparing two groups using Bertalanffy group model, and I said, okay, if one parameter is common. Now, another possibility is when two parameters are common. What are these two parameters? We're also going to have 3 possibilities. The 3 possibilities what you have here. You know, when you compare the parameters on a pairwise level, the number of possibilities is going to be 3. The first one is going to be when L infinity and K are common. What are you going to see? You are not going to see group attached to L infinity and K, but you're only going to see group attached to C0. Look at that. That's so beautiful. What about when L infinity and T0 is common? You are not going to see group attached to L infinity and T0. You're only going to see group attached to K. What about if K and T0 are common between the two groups? Okay, the same. Look at that. Then What is a common model? Oh my God, the common model now means they got the same value for L infinity, the same value for K, the same value for T0. That is what we call common model. Any question? These are the possible models that we can talk about when we want to compare two groups using the Van Bertalanffy group model. Now, where do we start from? I told you, we're basically I'm going to show you the outcode now. We're basically going to start from the general, but let me tell you, we're going to use common for general. You know what is common? When the two groups have the same L infinity, they have the same T0, and they have the same K. So if you take a look at what I'm doing here, I'm doing the one for common. I want to get the initial values. And when I get the initial values, you know, for common, it means I'm actually going to replicate that. Okay, replicate that for two groups. Okay, and that was why I said the general model requires starting value for 6 parameters. You know, 6 parameters, but I'm going to use the idea of common here, right? Where I'm only going to get 3 and it will be repeated. Okay, and that was why I said, however, starting value for the common parameter in the common model can be generally be used for both group model. And that was why, if you take a look at what I'm doing now, what am I doing? I repeated. Okay, I repeated. Now, when I repeated, then I first want to run that of the general model. Why do I need to start from the general model? Because I need to investigate whether assumption hold, assumptions of normality, and assumptions of the constant variance, whether it's hold with the general model. And that's why I'm first going to run the general model. If I want to run the general model, of course, you know, this is the way I'm actually going to specify that. Okay, you can see L infinity on 6. Okay, and you can see K on 6. You can see TO on 6. Okay, which means I'm trying to say, okay, the two groups have different value, but don't forget, I use the idea of the common for general, because on the normal ground, I'm supposed to get different value for the 6 parameter, but we can actually assume, use the idea of common for the general, and we can actually replicate, okay? So by the time we now fit that general now, with the data that we have, using the initial values that we got from the first code, we can now conduct diagnostic testing, where we want to investigate whether assumptions are violated. Now, of course, this is the code, and this is what I have now. Oh my God. Okay, this is looking promising, right? Okay, it's actually looking promising. Don't forget the data set I'm using here. I'm using the combined data for male and female. That's what I'm using at the moment. I'm using the combined data for male and female. And of course, this is looking promising in terms of whether constant variance assumption is violated or the normality assumption is violated. Take a look at this. This is looking promising. There's no violation here. Then from there, the next thing I want to do now, if the general model, if the assumption is not violated in the general model, we don't need to conduct you know, test of assumptions on the other submodules. Okay, we're actually going to use the principle of mathematical induction. We're going to say, okay, since the general model is fantastic, then I don't need to investigate assumption violation with the submodules. Now, this is the code for all the submodules. You know, I specify the modules the other time. when one parameter is in common, when two parameter is common and when they have separate parameter. Take a look at that. When you take a look at all this code here, okay, one is to get the initial value, the other one is to run the model. Okay, so take a look at that. If you take a look at the first one is trying to say VB1KT. I want to get the initial value. VB1KT means they have one parameter in common. What do they have in common? L infinity. They have L infinity in common. When you see KT, when you see LT, it means they have T0 in common. Oh, sorry. No. When you see LT, they have K in common. Does that make sense? When you see LK, L and K, they have T0 in common. And that was why you see me indicating 1, 1, 1, 1. What do I indicate? 1, 1, 1, 1, 1, 1 indicate they have one parameter in common. When I indicate 1 and I just write two other variables, two other parameters, the one that is missing there is what the parameter that is missing is the one they have in common. Does that make sense? Then I'm going to do the same thing to 2. Oh, when I want to write, they have two parameters in common when you see T. Okay, if you take a look at the VB2T now, the one of the VB2T is trying to say they have other two parameters in common. What are the parameters other than T? That would be L infinity and K. Does that make sense? Okay, that's what the 2 is talking about. Okay, then the last one, okay, common parameter is when they have all the parameter common. So these are the code for the possible subset model. Now, when I have the code, how do I start? Okay, I'm actually going to start from the first one. When you take a look at, I want to start with when they have common K and T0. If when you take a look at the first one that you see, when you see 1LT, what is missing? K, right? It means they have K in common. When you take a look at the second one, 2L, 2 in common, you have L, right? Then what is missing? What is missing is actually K and T. Does that make sense now? Now, we got 2. So take a look at that. Okay, now, these are the code now, if I want to run. The first one, fit1KT. What does that mean? They have one parameter in common. What was the parameter? L infinity. The second one, fit1LT. They got one parameter in common. What is missing? That's a K, right? Fit1LK. They have one parameter in common. What is missing in LK? That's T0, right? Take a look at that. Then when you get to fit2T, they got two parameters in common. What is missing? When you have a T, what is missing? L infinity and K. Fit2K, they got two parameters in common. You can see K, what is missing? L infinity and T. Then fit2L, okay, they got two parameters in common. You can see L, what is missing? K and T. Then the last one, fit common, okay, or they all have all parameters in common. Okay, so you're going to fit that. Now, this is what we're going to do. When you fit all of them, how do we find the subset best model? We're actually going to go hierarchical. We're going to start comparing the general where they have separate parameter in common with when they have one in common. Then I'm going to proceed to when they have two in common, and I'm going to proceed to when they have all of them in common. That's exactly what I'm going to do. I'm actually going to be using AIC, or I can use the ANOVA F test. Take a look at what I want to do here. What am I doing here? I'm doing ANOVA fit1KT, fit general. Fit 1 KT will be the simpler model. Fit general will be the complicated. The complicated is when they have separate parameter, the two groups. But the simpler one is, what do they have in common? When you see fit KT, okay, you're actually going to see they have L infinity in general. Now, when you take a look at the code, this is what is going to come out. Now, what is the p-value? You know, your HO here is supporting fit 1 KT. Your alternative is supporting fit general. You know, we use this is more or less like ANOVA, nested ANOVA test, right? That we have actually used in linear regression. Now the p-value is 0.12. So what are we we're gonna fail to reject, right? So what is better? The fit 1 KT is better than the fit general. Does that make sense? The fit 1 KT is better than fit general. Then I'm going to proceed to the next one. Now in the next one, I want to compare, you know, fit KT. Okay, fit one that you see means they have one parameter in common between this guy and the general. The parameter they have in common is L infinity. That's what is missing here. Then I'm going to compare fit 1 LT against with general. Look at that. Okay. And LT, what is missing here, right, is K, right? K is missing, right? Okay. So want to see whether they have K in general, K in common. What is the p-value? 0.52. Okay. We're also rejecting fit general here. We rejected fit general the first time. We rejected it again here. Now, the next thing we want to go into now is other possibility. Don't forget, when you're talking about one common, there are three types of one common, right? Okay. One common, number one, fit 1 KT with general. Maybe what is common is L infinity. And fit 1 LT with general. Maybe what is common now is K. Then the last one, what is common, you know, fit 1 LK with fit general. What is common is T0. If you take a look at in each of the tests that we conducted, we actually rejected general. Any question? We rejected general. Don't forget the complicated general will be in the alternative. Why the simpler one will be in the non-hypothesis. And that was why I said this result indicates that each one parameter in common modus fit data well more than the general. You can see we rejected general in the three possible model the test that we did. And I said that because each one parameter in common model is simpler than the general model, then the general model will be removed from the consideration as the best model. So thus at this point, it is known that separate value for all the three parameters are not needed for the two groups. When you reject general, you are nullifying the idea that separate parameters, okay, are needed. You don't need separate parameter for the two groups. Any question? So far, so good, right? Okay. Now, do you know what I want to compare now? I'm now going to go to the two parameters in common. Okay. You know, what are the ones that are fantastic? The one parameter in common, fantastic, right? Okay. You know, why am I using LK? One parameter common LK. Let's go back. We're going to see now in each of the tests, the one that have a larger p-value. If you take a look at the p-value is 0.12, the p-value here is 0.52. Oh my God, the p-value here is 0.73. If I'm going to choose between one common parameter in common, I'm actually going to choose this guy. What is this guy? Fit 1 LK. And that was why in my next consideration, what did I choose? From the one parameter in common, I choose fit 1 LK. So what I want to do now, I want to compare two parameters in common with the best model for now. The best model for now is fit one LQ. Now, is there anybody who want to ask question about why I consider fit one LQ instead of fit one maybe TK or whatever? Because it has the largest p value. Okay, go ahead, go ahead. Oh, I understand what you mean. Like the one we did in linear. I think we don't do that. Yeah, we have to go hierarchical, where we start with the general. You know, the one in the linear one, we start with simplest model. You know, so but here we're going to first start with the general. Yeah, that's a good question. Very good question. Okay, now when I fit now in the non-hypothesis, fit two, the two in common, it will be the simplest. Of course, you know, two in common will be simpler than one in common. Does that make sense? And the two in common will be under the HO. Okay, so when I compare that now, I fail to reject, which means fit two in common is better for now, right? When you look at the 0.18, we fail to reject the hypothesis of fit two in common. What is it? What is that? What are those parameters that are common? That would be, you know, you can see fit to L here, right? That would be K and T, K and T0. Does that make sense? Now, I'm now going to go to the next one. What am I doing now? I'm also going to compare the other two common with the one common. Okay. When I do that, this time around, do you see what happened? We actually rejected the non-hypothesis. Okay. And this is now in favor of fit one LK. What is it meaning? Fit one LK means, what do they have in common? They got T0 in common, right? Now, and that was why I said, if you take a look at the first one I did, I said the first result suggests that the model with K in common fit the data well, okay, as model without K. If you take a look at the first one, model with K and model without K, that was what we did in the first one. The model with K, the model without K, okay? Now, and the second one indicate that model without L infinity, okay? The model without L infinity in common fit the model better with the L infinity, with the one with the L infinity in common. Take a look at that. That's what we have here. Because if you take a look at that, L infinity, no sex, L infinity with sex, okay? It means you have one with L infinity and another one without that. Now you can see what we have now. Now another consideration, you know, up to this moment, we're still fitting this guy. Then we're going to consider another one. The finally is comparing the most common, the model that have all the parameters in common. Of course, the model that have all the parameters in common would have been the best, like what we want, because we don't need to worry too much here. And that's why it's under the non-hypothesis against our fit to L. Okay. Now, by the time we actually analyze that, the p-value was this. And that was why I said this result show very strong evidence that common model, okay, does not fit the data. Of course, because the common model was what we stated in the non-hypothesis. And that has been rejected because of the p-value that you have right now. And I said, does not fit the data better than the model with a separate L infinity. Okay, when you take a look at the second one, the fit to L, model with a separate L infinity, you know, fit to L, separate L infinity means they have, what do they have in common? They have K and T0 in common, but separate L infinity. That's why you say fit to L. So anytime you say fit to L, okay, it means what you don't see as part of the parameter is what they have in common. What you are saying, okay, is what they do not have. So that was why I said the results show very strong evidence that common module does not fit that well, and thus module with common K and T0 parameter but separate L infinity is a module that we're going to choose. Now, what is the conclusion general? Oh my God, the conclusion in general is that the best module is the module that has separate asymptotic mean length, L infinity, but they have the same, the two group have the same K, they have the same T naught. Does that make sense? But they have the separate L infinity. But what if I don't want to go, through this? Can I have another way to go? Another way to go is I'm going to fit all the modules. Then I will get the AIC of all of them. The one with the lowest AIC is what I'm going to choose. There's another way to choose that. And this is very similar to what you told me the other time, but instead of using ANOVA, we're going to use AIC. So which means you are very close. Good job. In the end, which one has the lowest AIC? Okay. If you take a look at what we have, yeah, it's going to be Phi2L. Don't forget, the Phi2L was what we choose here using the hierarchical nested ANOVA test. But if you go by the smallest AIC, but before you run the AIC, you need to first run all the model. I think I've shown you how to run all the model here. There's a code here. Look at that. Then when you run off this, it will be very easy, okay, for you to be able to get the AIC of all the models. And the one with the smallest AIC correspond to Phi2L. The Phi2L is trying to say, the Phi2L is trying to say, I'm actually going to fit module that have two common parameters. What are the two common parameters we're talking about? When you see Phi2L, other parameters that are missing, A and T0, but they're going to have separate L infinity. And you know what? That is a module that I'm actually going to fit at the end of the day. Now, I want to fit the best module now. Oh my God. I'm just going to write overview of Phi2L, and I'm going to have these results. Any question? Go ahead. Yeah, I can see what you're trying to say. They have the same. That's another good question. That is where the degree of freedom will come into play. You know, I love that question that you asked. You know, the degree of freedom is very, very important in statistical analysis, and that is why we don't just run this AIC based on the result on the AIC. It's better we go through standard statistical tests. Does that make sense? Because that may be confusing, just like this now that the Phi1 KT, the Phi LT, or the Phi1 LT and the Phi1 LK and the Phi2L have the same AIC. Okay, now, like I said, that's what I'm going to run. And the moment I run that, because I want you to pay attention to the results. What do you see? You're actually going to have two different values for L infinity. Of course, we say separate L infinity, but the two group is only going to have the same value for K, which is 0.2372 here, and the same value for T0, which is a negative 2.2583. Can you see that? And we can at the same time look at the confidence interval. Of course, you know, in statistical analysis, how do we how can we rely on the point on the mean, on the point estimate? We need a confidence interval, right? If I really want to know how the survey that I conducted reflects the overall view of the population, I need a confidence interval, right? Now, this is a asymptotic confidence interval for the parameters, and this is a correlation matrix. But let me tell you the problem that we have. The problem with the growth model, the problem of independence. If you take a look at the correlation matrix now, you're actually going to see that the relationship between two different parameters is very, very huge. This is not unexpected because we're working with a time series data. Assumptions of independence will be violated. Now, but let me tell you what we're going to do next. What we're going to do next is what we call Francis parameterization of von Bertalanffy models in 1998. In fact, before 1998, several biologists, scientists, they tried to reparameterize von Bertalanffy group model. Why? Why do you think they want to do that? Francis in particular attempted to reparameterize that because of the fact he realized that the parameter that he estimated using von Bertalanffy growth model with length to time data is different from what he got when he used a tagging data. You know, in fishery, in ecology, has any one of you heard about capture and recapture method? Capture and recapture. You know, if I really want to know whether some animals in the bush, whether some of them they will become extinct, or if I basically want to estimate the numbers of animals in a bush, or I want to estimate the numbers of fish in a river, that would be difficult to do. Like if I just go into a river, I want to count the numbers of fish that I have, but they can use a tagging, okay, tagging method or tagging, okay. The tagging method, we use what we call capture, recapture. What do I mean by capture, recapture? They're going to capture some fish at random. They're going to tag them. They're going to tag them. You know how to tag them, like mark them. They're going to release them. And maybe after some time, they're going to go into, that population again and randomly select fish. Then in the second occasion, they want to be able to see how many of those ones that were tagged in the first occasion were included in the second occasion. Okay, that method is what we call the tagging. So what Francis observed in 1998 when he was trying to use von Bertalanffy growth model, he used the data set that is based on length and age, and he used a data set for tagging, the one from tag. He realized that the parameters are not compatible. Does that make sense? He realized that the parameters are not compatible, and what Francis did is to reparameterize, like trying to remodify von Bertalanffy group model. In the next lecture, we're actually going to see how Francis did that, and was there a benefit, like statistical benefit from Francis reparameterization of von Bertalanffy group model? We're going to discuss that in the next class. And we also want to see in the next class whether the reparameterization of von Bertalanffy group model by Francis whether that may fix independence assumption, we also want to see. And how are we going to know whether it fits independent assumption? We can construct the correlation matrix and see for ourselves. Any question? Any question? In the absence of question, make sure you stay safe and enjoy the sunshine. See you on Monday. Bye for now, everyone.